Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Zürich. Quick thanks to our sponsor, the National Center of Competence in Research on Dependable Ubiquitous Automation and the International Federation of Automatic Control. Our guest today is Davide Scaramuzza, professor of robotics and perception at the University of Zürich, where he leads the robotics and perception group. Welcome to the show, Davide.
Thank you, Alberto.
So it's an honor and pleasure to have you here today. We are definitely have to talk about a lot of things, among which event-based cameras for sure, and agile flying with drones. But maybe before we start, in doing my homework, I was looking at your curriculum, and I was struck by the fact that you do have a passion for magic. So can you tell us what does magic have to do with robotics, or if they do?
Actually, it's a very good question. And I think they do have something in common. Because in robotics, basically, you want to build systems that are autonomous, that basically move by themselves. And in magic, you also want to make objects basically behave as if they have their own soul, so they can move by themselves. So they share something in common.
And what's your favorite type of magic?
My favorite type of magic is a close-up, which is usually done with the cards, coins, and ropes.
And the only trick that I know is the disappearing coin trick, but I guess that's the most basic. Do you have a favorite one?
I do. It's the ambitious card. It's a card that always comes to the top of the deck, wherever you put it in the deck. Okay. And it's signed.
Okay. I didn't know this trick, but I will definitely look it up. And the magician who inspired you along the way, do you have a favorite one? Or?
Yeah, actually the magician that brought me into this field of magic was David Copperfield. When I saw him the first time on TV, I said, oh my God, how does he do that? And so I wanted to learn that.
The only thing that I remember about David Copperfield is him like heading towards the Niagara Falls, locked into some basically, I don't know, yellow thing, and he was managed somehow to get out just before falling. It's kind of crazy.
Yeah, what I like about David Copperfield is that he revolutionized magic because he ventured into the impossible. And I think this also is something that I like a lot about robotics, trying to do things that seem apparently not achievable.
Okay. And so is that what attracted you? That was actually my next question. What was it that attracted you towards the field of robotics?
I was always attracted to robots since I was probably 3, when my father took me to the movie theater to watch one of the Star Wars movies. And but then it was actually when I studied electronics engineering at the University of Perugia that I started to really become interested in robotics. And actually my first experience in robotics came with a master thesis, which was about visual SLAM-based navigation of a two-wheeled robot.
Yeah, so that's essentially the topic where you started. So right. SLAM and mostly vision for robotics. And so that led you to start a PhD with Roland Siedvard, a giant in the field of robotics. Can you tell us a bit about your inception, if you want, into the field?
Yes, indeed. So after the master degree in electronics engineering, I basically applied for an internship with Roland Siegwart. At the beginning, I wasn't sure I wanted to actually pursue a PhD. And during those months at the Autonomous Systems Lab, I really became fascinated with robotics. So I was 100% sure that I wanted to really delve into the field. So I was involved in a perception task. I was one of the few people at that time working on cameras, which then nowadays is one of the main sensors actually used on robots. But who could have ever predicted that at the time? So it was in 2004 when I started my PhD, and I was initially on vision-based localization, mapping, and autonomous navigation using a single camera for self-driving cars. So we had a smart car at the time equipped with different sensors, and my task was about actually seeing what was possible to achieve using just a single camera. Then in 2009, Google announced the self-driving car project, and then it became clear to me that probably self-driving car was actually now moving from academia to industry, and it was probably time to look at different things, more exotic things. And so I discussed with Roland, and then we saw that there was an opportunity to actually bring visual SLAM and computer vision to the third dimension, and that's when actually I started working on drones.
Okay. So that's, an excellent introduction into your journey. I just want to maybe clarify a couple of things and then maybe just move forward towards flying. So one thing is, what is actually SLAM? Just for our audience, I would describe it as basically constructing and updating a map while also tracking the location of an agent. And the other thing was that you actually had a real smart car. It was a real car. Okay, and so you mentioned that in 2009, you veer off towards the world of drones. So first of all, I have maybe a minor question, but I never really understand what is the difference between a quadcopter, a drone, and an MAV, micro aerial vehicle. Are they all the same thing? Are they different?
So a drone is basically the superset that contains all the other ones that you mentioned. So a drone is basically an unmanned aerial vehicle.
Okay.
The word drone comes from the German word drone, which which actually refers to the male bee, and it was used to refer to an unmanned aerial vehicle only in 1919, so more than a century ago. And then an MAV is an unmanned aerial vehicle, so a drone that is usually small and weighs less than 5 kilograms, and it's less than 2 meters in size. However, often it's intended even as a smaller UAV, like nowadays when we think of a quadcopter, so a four-rotor drone, we think of the same hobby drones that we see around when we go on vacation, flying around us, so about less than a kilo in weight and less than half a meter in size.
Okay, so size is really what determines these sets.
Size and weight.
Size and weight, okay. So you mentioned that in 2009 you moved towards drones, and I guess this coincides also with this DARPA challenge.
No, if you want, I can explain. In 2009, basically, we started a European project named sFly, that stands for Swarm of Microflying Robots, and it was the first European project to investigate the use of onboard cameras to navigate drones in GPS-denied environments.
Okay.
So basically, that was basically the initiation, the first motivation to start working on this. The DARPA project you are referring to came only in 2015, and the program I was involved in is called FAST, Lightweight Autonomy Program, FLA, and it was a 3-year project that was about developing computer vision and navigation algorithms to fly drones as fast as possible without GPS, but just using onboard cameras and inertial sensors.
Okay, so I guess maybe the obvious question for those who are not in the field is, why is flying without a GPS difficult?
Flying without GPS is difficult because you have to use your onboard sensors. So what makes navigating with GPS easy is that you're relying on an external constellation of sensors, GPS, of which you know perfectly their position, that reliably send the information about their position, and then your GPS receiver basically is able to triangulate the position of the agent within a certain tolerance. The problem with GPS is that it's not available indoors, and even outdoors is not reliable, especially in proximity to buildings. So that's why if you want to have a drone navigating close to buildings or inside buildings or even outdoors under the tree canopy, for example, so in forests, it's very important that you use onboard sensors. Now, when you look at onboard sensors, the only choices available are radar, LiDAR, and cameras. But the problem is radar and LiDAR are active sensors, so you have to emit energy in the environment, which means you have to basically consume between 10 and 20 watts, which basically subtracts energy to the one you need to fly, even though 90% of the energy usually required by drone is used to fly. But then another problem they have has to do with the poor resolution of these sensors in terms of angular resolution, and also the weight. For example, a LiDAR can weigh up to 1 kilo. Also, we have to think about the cost. Now, when you put all these things into account and you want a drone that is safe and that can fly far, then you want a drone that actually uses as lightweight sensors as possible. And in this case, the only viable solution still nowadays is actually to use cameras. One or multiple cameras, potentially with an inertial measurement unit, so an accelerometer and gyroscope, in order to provide not only redundancy but also an additional point of failure. And then the algorithms will revolve around basically first mapping the environment, so that you can localize the drone within the map. So that's SLAM, what you correctly explained before. And then you need algorithms of planning and control in order to plan collision-free trajectories and execute these trajectories.
I'm definitely interested about talking about the control part at some point later. But before, maybe I'd like to clarify one thing that I didn't understand. So normally the processing unit for these drones is on board as well, or is it outside?
So if you want the drone to be completely autonomous, then all the processing must be on board.
Okay, so we're literally talking about an fully autonomous
Fully
machine.
autonomous machine, that's correct.
Okay.
Yes.
Okay, and the second clarification that I wanted to ask is regarding this sFly project, because I was watching some videos while preparing this show, and it must have been amazing to be the first to demonstrate vision-based autonomous flight. I mean, that's according to my record. I don't know if I'm...
That is correct. So to our knowledge, basically our team, when I was still a postdoc with Roland Sigvart, was the first to demonstrate the first vision-based autonomous flight. It happened while we participated in a competition organized at TU Delft called the European Micro Aerial Vehicle Competition. And there they were asking teams to basically take off from the floor of the gym of TU Delft, navigate 10 meters, enter a small mock-up apartment through the window, recognize a picture, and then either land or come back. And our team demonstrated that we could do this completely autonomously, while all the other teams were actually using FPV. So there was a pilot in the loop. It was only 10 meters of navigation that we did. So then we passed through the window and then we crashed inside the apartment. But it was 10 meters that basically were historical, because we didn't expect at that time that then this technology called vision-based navigation would have so much impact, because nowadays, 13 years have passed since that event. We can find vision-based navigation on Skydio drones, DJI drones, Parrot drones, and even on the NASA Mars Ingenuity helicopter, which uses a technique similar to what we were using in 2009, basically a Kalman filter that fuses information from the National Measurement Unit and Visual SLAM.
You're anticipating my next question, which would be, what was it that actually made you make the leap somehow? So was it a technological advancement, or was it in terms of algorithms or putting things together?
It was all of the three things that you mentioned combined. So in 2008, I was really astonished by the advances of visual SLAM, monocular SLAM, so with a single camera, no IMU. I had the chance to participate in the European Computer Vision Conference in 2008 in Marseille. It was my first vision conference. I was coming from a robotics background, so I was only attending ICRA and IROS. So typically there were not papers about what I would see then at this European Computer Vision Conference. And I remember that the first author of this paper, called PTAM, Parallel Tracking and Mapping Done in Real Time, demonstrated on stage during his oral presentation something that was really amazing, that was mind-blowing. So he was really able to map the entire room, actually the entire auditorium, with a single camera in real time in his laptop. And that PTAM piece of software was then made available open source. And then when I returned home, I asked Roland, hey, what do you think about this? We should put it on a drone. What do you think? And then he said, yes, let's do it. Actually, we can write a European project about it. And so first we designed a prototype together with a team of PhD students and bachelor students. And then we only demonstrate that we could actually first take off, hover at 1 meter from the takeoff spot, move 2 meters away, and land in another spot. At the time, the computation was not done on board. It was done off board using a long USB cable that was connecting the onboard camera of the drone to a laptop, but it was basically the very first. So it was everything. This was made possible by the advances in Visual SLAM, by integration, system integration, of course, because in the end we put together a loosely coupled Kalman filter that was then fusing information from the molecular SLAM with the inertial measurement unit, because molecular SLAM doesn't give you the absolute scale. It tells you how much you move with respect to the first displacement, but it's only relative displacement. So if you want to have information in the absolute scale, which you need to control the drone, then you need the information in meters, position information in meters. So you can only get that from the IMU that measures accelerations in meters per second squared. Right, so if you double integrate the acceleration, then you get the position, but it's of course drifted compared to the vision. Now, if you fuse this information with the vision, then you get both the absolute scale and you correct also the drift of the IMU.
Phenomenal, fantastic. Just a curiosity before we move on, and that would be related to the implementation actually. So when you say we built up a prototype and we demonstrated that we could actually move for 1 meter, how much time does it actually take normally, or and how many people, what sort of expertise is needed?
So at the beginning, we basically we had different bachelor and master thesis focusing on different things, because it was the first time that they were actually addressing this problem. So one person investigated, for example, the Kalman filter-based sensor fusion between the camera and the IMU. Another investigated, for example, the target detection for high precision takeoff and landing. And then another one also looked at other aspects, especially the integration on the quadrotor, the ROS implementation. ROS was the robotic operating system, which had just come out, by the way, and there were also a lot of issues. Then there was another student that was actually dedicated to the hardware itself. So quadcopter drones started to become a thing only in 2007. I saw my first quadcopter flight in person at RSS, Robotic Science and Systems, which was a conference at the time that took place in Rome. And a German company called Ascenti Technologies was demonstrating that in front of all the audience. Then actually that was the first company we asked to be our partner in the European project sFly. So you see, all the pieces of the puzzle then now make sense. All these people then became part of the same team. But so it was everything. So it was a team of 5 people.
Okay, so definitely you need knowledge from all sorts of fields in robotics. That's what makes it so fascinating, at least
That's
for
correct. We need expertise in mechanical engineering, control, and electronics engineering, and computer vision.
It's huge. Okay, so now I'm imagining yourself when you actually successfully demonstrate autonomous flying with which is just vision based. What was the next step for you?
After we demonstrated the first vision-based autonomous flight, the next step was actually to make drones fly rather than just navigate in near hover conditions. So the first observation that I made was that these drones, these autonomous drones, were not navigating like human pilots would actually fly them. They were basically, for me, levitating. That's another comparison to magic. There is a difference between flying and levitation, which David Copperfield made very clear in 1993 when he made the first flight on stage. So you see, when drones were flying autonomously, they were flying straight line trajectories, or waypoint, from waypoint to waypoint in straight line. But that is very different from the way that humans fly drones. We fly smooth trajectories when we fly drones. Doesn't have to be acrobatic maneuvers, but we just fly, very, very smoothly. By contrast, drones were basically navigating as clumsy robots. They were basically moving, straight lines. So how could we make that step? To make that step that now we call agile flight, Basically, we needed to advance in perception, planning, and control, because if you want to navigate faster, more agilely, then obviously you need to perceive faster and you need to think faster. So you need advancements in both ways. So perception, planning, and control side. So that's when we started also to move away, for example, on the control side from PID to model predictive controllers. And then when we started to move also away from SLAM-based only navigation, which nowadays we only call vision-based state estimation, to perception-aware planning and control, because you also need to take into account where you are looking at in order to facilitate the perception task, which you are using for state estimation after all. And you must do that without thinking. We learned that.
This is super interesting. It's something that I would like to dig into. Maybe just before we do that, I'd like to understand what are the actual control techniques that are mostly used in drone navigation. Because my question would be, if drones before were just levitating, could have been just a problem of the control, plan and control part, or was it also a problem of something else?
It was also a problem of the control part, using PID controllers. So another leap forward that we made was to adopt MPC. Of course, coming from ETH, we were first exposed, by the course of Manfred Morarid and his legacy. So it was an easy choice. So we actually started using MPC, I think, in 2016. That's when we moved away from PID, and that's when we started to observe a quick change in the navigation and the maneuvering of our drones. But the problem with MPC is that you have to solve basically planning and control simultaneously, and you want to do this on board while you are controlling the drone. So typically we will control drones at 50 Hertz, which we still do today, by the way. I mean, sending the high-level commands at 50 Hertz, then the low-level commands are sent much faster at over a kilohertz. But so that means that you needed to solve this optimization fast. And that's where actually we started to explore the world of Akados and Professor Moritz Dill at the University of Freiburg, which implemented solvers that are super efficient, and they implement MPC in real time thanks to so-called real-time iteration that basically solves the optimization while the controller is already executing the trajectory.
Okay, super interesting. So basically this is essentially what leads you towards the path of agile flying, finally. And I see that, I mean, you've been doing amazing work in all directions about robot acrobatics, robots that navigate in the wild, and robots that compete with actual humans in drone racing. This has actually made the cover of Nature very recently this year. Is there anything that you would like to talk about now? I think it would be nice maybe to talk about drone racing in this respect, because it's definitely fascinating.
Yes, I would like to talk about drone racing because many people ask me why drone racing and how do you think that drone racing research will transfer to real world applications? Because let's be honest, drone racing is just a game. Eventually, we want drones that can be used for the good in many civilian applications, from delivery to inspection tasks, search and rescue, and so on. And so why drone racing? I would like to actually start with that. So let's start with an observation. The battery of a multi-copter drone usually lasts for about half an hour. If you use a fixed wing drone, so then it's a different thing. You have the lift, and then the drone can fly much longer, but it's a different story. So now let's talk about multi-copter drones. Only half an hour battery life. So of course, there are advancements that are being made there on fuel cells and lithium sulfur cells, batteries that will actually be used in the near future. But there is another thing where we can advance, which is actually to make drones fly faster, because a drone that flies fast can fly farther. Of course, if you fly too fast, also you start drawing more energy from the battery. You also start encountering more air drag, which also starts to actually slow down your drone, and so it's no longer convenient to fly that fast. But we have a study that actually computes basically the speed, the distance that you can fly a multi-copter drone with a given battery, with a given mass, with given aerodynamics, given propellers, given motors, as a function of the battery, and you can compute how far the drone can actually fly before the battery completely dies. And what we observed is that it's a parabola that basically has an apex. So that means, what is this parabola? This is basically the trend, so the plot that shows how the range in kilometers changes as a function of the flight speed in meters per second. And what we observe is that there exists an optimal speed for every drone. Given a drone, you can compute an optimal speed for a given trajectory. For example, for a DJI Mavic drone, we computed that the maximum distance you can reach before the drone battery is completely depleted is 3.5 kilometers. If you fly any faster than, it's 3.5 kilometers, and you reach this optimal speed at 6 meters per second. But if you fly any faster, it's no longer convenient to fly that fast, because actually then you reach lower distances. So how do we go from here to drone racing? Now, if you look at the current landscape of commercial drones, none of them flies drones at the optimal speed. So now I'm thinking of DJI drones, Skydio drones, flyability drones. These are some of the world leaders in inspection tasks in where they are leaders. And so actually they fly at speeds that range from 0.5 meters per second to no more than 1.2 meters per second. Why? Because if you fly too fast, you start experiencing motion blur, and you also need to think faster, so you need to have fast algorithms, you need to react faster, and so on. So there are many issues that have to do with motion blur, robustness, and safety, which are actually very, very strong issues. But from a research point of view, basically our study tells us that one day, whether this happens in 5, 10 years, or 20 years, we will have drones that will fly for all these tasks at the optimal speed in order to maximize their utility, their productivity. So we need to push that. And from this, how can we actually push research to work on agile flight? So we thought about it, and we came up with a competition, with a game, to basically incentivize researchers to push the boundaries on vision-based navigation. That's where the idea of drone racing came up. Coincidentally, at IROS, which is the International Conference on the Robotics and Intelligent Systems, in 2016, Professor Yoon-Pil Moon from South Korea started to organize a series of autonomous drone racing competitions that took place from 2016 until before COVID in 2019. And we also started participating in there. And we actually realized that it was very, very, very difficult. If you think about it, 2016, when we participated, 2017, when we participated in the first IROS drone racing competition, we were flying at 3 kilometers per hour. No, not even 1 kilometers per hour. The year later in Madrid, IROS Madrid, we raced and we won the competition flying at 3 kilometers per hour. In 2019, we participated in the Alpha Pilot competition organized by the Drone Racing League. By the way, all these competitions were between autonomous drones only. There was no human against machine. And at the Alpha Pilot competition in 2019, we could fly at 30 kilometers per hour. But then it became clear that the next step should be, we should really try to challenge the humans, but not whatever human, ideally the world champions. And that's where actually the whole challenge started. So since 2019, we have been pushing very, very, very hard to achieve this goal. And so that was also thanks to the European Research Council, who gave me the generous grant of 2 million euros as a consolidator grant to focus on this. And one of the milestones was indeed beating the world champions of drone racing.
And we definitely want to dig into this more because it's a fascinating story. I was just thinking that it was very convenient almost that drone racing is by itself a sport already, which exists already. And it's basically a televised sport where competitors are flying at high-speed aircrafts in a 3D circuit. So in my mind, I have these milestones. So in 1996, there's a Deep Blue versus Garry Kasparov. Then in 2016, we have the Google DeepMind challenge between Go players. And now in 2023, we see Alpha Pilot defying humans in flying drones. So
not Alpha Pilot, but Swift. We call our algorithm Swift.
Swift, okay. So can you tell us a bit about this, how this story unfolded?
Yes. So in 2019, basically, after participating in the Alpha Pilot competition organized by the Drone Racing League, basically we basically reflected on the lessons learned from this competition. So there, our maximum speed, as I said, was 30 kilometers per hour. And we said, okay, how can we improve that? So we need to improve at every level, in perception, planning, and control. And so we started working on classic optimal control algorithms, and at the same time also to improve our visual inertia state estimation based on visual inertia SLAM. So single camera plus IMU, inertial measurement unit. So first of all, let me talk a bit about the state estimation part. There was until 2017 one of the biggest core researches on my lab to improve the state estimation, but we were not that flying until that time that fast. It was then in 2019 we started to actually observe the deficiencies of visual inertia SLAM at high speed. Why? Because at those speeds actually you have motion blur. And that's where visual SLAM actually fails, because of motion blur you can lose the features that you need to estimate your motion. Also, the IMU, especially gyroscopes, experience quite a large drift, not much the accelerometers, because actually at high accelerations they have a high signal to noise ratio, but actually the gyroscopes drift there. So you have these problems, and what we didn't expect is that the drift of visual inertial state estimation flying at 20 meters per second, so at the speed of human pilots, which was over 80 kilometers per hour, would be 20%. Just to give you a comparison, when you fly slowly, up to 1 or 5 meters per second, you experience a drift of no more than 1 or 2%. That's also what Ingenuity experiences on Mars. No more than 2%. So 2 meters every 100 meters of traveled distance. But flying at speeds that go over 20 meters per second or 80 kilometers per hour, you experience 20%. So 20% drift every 100 meters of flown trajectory. There is not much you can do with that. You will bump into the first gate of your racing track. So we had to actually improve on that. On the other side, what we also realized is that we needed better control algorithms. So at that time, we were already working in 2019 on MPC, and we needed to improve that. So we realized that the big challenge was also the path planning. So how do you solve drone racing? Maybe first we can explain drone racing if you want, and then I can tell you what the different challenges are. So in drone racing, the goal is to pass through a sequence of gates in a given order in minimum time. You win if you can reach the finish line earlier than all your opponents.
And the map is known.
And the map is known in advance. That's very, very important, actually, you bring it up, because human pilots are disclosed the map already weeks before the competition.
Okay.
Not only, but they can actually access the racing track for several days. And leagues like the Drone Racing League even provides a CAD file to the competitors. Yes, because they can actually practice using the Drone Racing League simulator, which is a quite realistic simulator, including aerodynamic effects. So they get a CAD file that they can import and then fly as if they were flying in the real world. And then they get some practice time with the real drone.
It's literally like in Formula One. I mean, I don't know whether they do practice as well. They probably do practice also on simulators, and they also have some practice tests on the actual circuit.
Correct. Indeed, the Drone Racing League simulator is also used by the Drone Racing League to recruit pilots, by the way. And there are also other simulators like Liftoff. And we started the collaboration also with Liftoff, by the way. So basically, how do you solve drone racing? So since you know the map a priori, well, all the technological pieces are actually already there. So we can basically plan a trajectory from the start to the finish in minimum time.
Sure.
And we realized that actually at the time we started working on this topic, which was in 2019-20, there was no algorithm that could solve this using the full quadrotor dynamical model. There were only algorithms that would approximate the trajectory with polynomials using the full quadrodal models, but polynomials are by definition suboptimals because, for example, they do not allow you to do bang-bang control, which is often what human pilots do. Yeah. And the other thing is, and they're smooth by default, that's a problem. And the other thing, or there was another set of algorithms that would assume that basically the drone is a point mass model, which is also another big approximation. So then my, at that time, PhD student Philippe Fern, who is now at Skydio, developed the first algorithm that can generate and compute numerically a time-optimal trajectory passing through a series of waypoints in minimum time using the full quadrodal model. And so we can do it. And we got super excited about it because this trajectory obviously is superhuman. Only machine can potentially fly this trajectory or not. And that's where also things became very, very interesting. So, by the way, how long does the optimizer take to compute this trajectory considering all the quadrodal dynamical model? Well, actually it takes up to 1 hour, sometimes even more than an hour, up to 3 hours, depending on the number of gates. Okay. By the way. So anyway, once you compute it, in principle, if you fly it, you will be superhuman. But that's where things started to crack. How do you execute this time-optimal trajectory?
Because now you have a reference and you want to use it, basically.
Correct. That is the reference trajectory. But that assumes that you have a perfect state estimator that allows you to be on the trajectory, on the reference trajectory. But the moment you drift off the reference trajectory, you will need to recompute the time-optimal trajectory. And notice that in drone racing, and that's why it's so fascinating, every centimeter matters. It can determine the win or the loss of the race. So you need to be really careful. So if you are off by a few centimeters from the time-optimal trajectory, in principle, you will want to regenerate a new time-optimal trajectory in order to, win against the human. Because especially I want to anticipate the difference usually between the first and second place winners in these competitions is a tenth of a second. So we are talking about 0.1 second. So every centimeter makes a difference.
Making my job very easy because that would have been my next question.
So, okay, then we said, okay, let's try to see what we can do if we have a perfect or near perfect state estimation from an external motion capture system. So first of all, we had to build an arena to allow this safe maneuvering at high speeds. So we rented, it took us many months to find a large enough space in Zürich. We found it near the airport of Dübendorf. It's a hangar, and there we set up, and we first bought an expensive motion capture system consisting of 36 cameras from the company Vicon. We installed them, we calibrated them, and we use this external sensor system to basically estimate the state of the drone, including position, velocity, and attitude, which was coming, by the way, at 400 times a second, okay? More than you can possibly do with onboard vision state estimation, by the way. And we observed that actually tracking this trajectory was not easy because of turbulences, because our minimum time trajectory planner was, yes, considering the full quadrodal dynamical model, but it was not considering, for example, aerodynamic effects, which are very difficult to estimate. And also it was not taking into account that there was a model mismatch between the model used in the simulator to compute the time-optimal trajectory and the real quadrodal. Yes, of course, you can do system ID, but remember again, here, every centimeter, every model mismatch can determine the win, the victory, or the loss of the race. Yeah. We are talking about tenths of a second. So you want to be super, super sure, and you want to do super perfect system ID. At the level of Formula One, everything matters. So that's when actually we realized that because of these model mismatches, we could not fly the time-optimal trajectory because in the real world, it would have been a different time-optimal trajectory. Okay. And then we also started to realize that turbulences were actually causing drifts by even 10 centimeters. So we started to realize that we needed to replan this time-optimal trajectory, but we couldn't wait 3 hours. So that's when my other PhD student, who then started that in 2021, Angel Romero, And I started working on replanning using MPCC. So the idea was to add a contouring term to model predictive control. So in model predictive control, typically you try to minimize the error with respect to a time reference trajectory. So in MPC, basically you tell the MPC that you want to be at this XYZ point at this given time. But that was actually a problem. That was a limitation. It was not an advantage. Because when you want to fly fast, yes, you want to follow your time optimal trajectory loosely, but at the same time, you want to maximize the progress along this line. Very much like Formula One pilots do. They try to maximize their progress along the center line. So that's where the MPCC came in, because we added a contouring term. So we are no longer tracking a time trajectory, but we are tracking a path now, basically a path of XYZ points. Okay, we don't tell anymore we want to be at that specific time, at that specific point. We want to track basically as close as possible to a reference path, but you can optimize and change, adapt the time in order to maximize the progress along this path. So MPCC actually was doing that. And but the problem with MPCC is that you still require a reference trajectory. And remember, this reference trajectory took up to 3 hours. Of course, if you don't change the gates and anything, in principle, you can stay with that. But what if you want to change things and so on? So Angel then started wondering, how actually is the MPCC performance depending on this reference trajectory? What happens if instead of using a reference trajectory, I use just a straight line trajectory between the centers of the gates? And surprise, surprise, actually, the result wasn't too different than when using the time optimal trajectory. So he made a time optimal replanner algorithm that uses MPCC to basically minimize the time to the goal. But now this one can be replanned in less than 2 milliseconds. So we went from 3 hours to less than 2 milliseconds happening on board. So we were super excited. So we started testing, integrating everything on the system. Remember, we were still using the motion capture. It was 2021. We invited the world-class experts, but not the world champions. I want to make the underscore here the difference. We invited world-class experts from Switzerland. They came and they competed against our autonomous drone that was actually not fully autonomous. It was actually relying on the external motion capture system for estimation, but nevertheless, the algorithms were basically running in real time. And we beat these two basically Swiss world-class experts. And we were super excited. We published a paper in Science Robotics and Robotics and Automation Letters and so on. But it was still relying on a motion capture system. But then we also started a collaboration with the Drone Racing League former champion, Gabriel Kocher, who originally Swiss, was actually at the time working for the Drone Racing League. And so he came from the US. And he flew the same racing track as the other world-class pilots from Switzerland. And we realized that actually, even using motion capture, and with our MPCC, the performance was behind this guy. Oh my God. So we observed two things. First of all, not every world-class pilot is the same. You really want to race against the best pilots. Second of all, why can't we beat this superhuman? Why can't we be superhuman even using motion capture? The problem, we didn't know it at the time, was actually this reliance on the reference trajectory. Now we know it after 3 years, but before we didn't know it. So, and that's the problem that we encountered with optimal control. In optimal control, basically, you are relying on this decomposition of the problem into planning and control. But basically what you're doing is that this decomposition biases, finally, the range of behaviors that you can actually do in order to control the drone. And that's where reinforcement learning shines, because basically it's able to discover trajectories without being biased by a reference trajectory. And it does so by trial and error. Also, we found out that reinforcement learning becomes more robust to degradations actually, of the state estimate, thanks to domain randomization.
Okay.
So let's try to recap the findings until then. We were able to replan time optimal trajectory super fast at 2 milliseconds time, but we were still relying on external motion capture based state estimation, and we could still not beat one of the best world-class pilots like Gabriel Kocher. So we needed to improve on two things: better controllers, but also do not cheat. We should not rely on motion capture. We should rely on onboard vision-based estimation, like humans do. Humans fly vision-based with a single camera. So we started reworking on our vision-based estimator. And then we realized that, besides, there was this problem I mentioned before, that there is a drift of 20%. Oh my God, how can we overcome this problem? Well, there is something we could use, which is that you know the map of the gates. You know perfectly where they are, let's say with centimeter or 10 centimeters accuracy typically. Because you install them by hand and you have to try to measure them by hand. So usually you make an error of 10 centimeters. But what you can do is to exploit a class of algorithms called PNP, perspective from endpoints. It is a class of computer vision algorithms that belongs to the class of photogrammetry that allow you to triangulate the position and orientation of the camera from at least 4 points in space. Okay. So if you ensure that the drone always observes at least a gate with 4 corners, you can always estimate the position of the drone. If you can detect more than one gate, then even better. So we integrated that, and we use a Kalman filter to fuse the information coming from the vision inertial odometry, vision inertial slab, plus the information coming from this PNP algorithm that was estimating its position also from the gates. So the vision inertial odometry is relying also on natural features in the environment, like from the ceiling, from the floor, people laying around, so whatever, natural landmarks. And the Kalman filter fuses this information. What we observed, though, is that there was still an error, of course. And the error actually ranges between 0.5 meter and 2 meters for state estimation. Okay. I mean, again, in a competition where every centimeter matters, well, that's a problem. It's a big problem. So we needed to find something around that. And we also realized that there were still aerodynamic effects and turbulences that we were not taking into account. Motor-to-motor interactions, and also turbulent flow that is caused because you are at that speed, you are flying in your own downwash. So basically the propellers emit air moving down and you're flying into the air. And you basically create vortices. We have a beautiful picture that we took by putting some smoke and flying the drone and then flashing a light at that specific moment. You beautifully see all these vortices being created. The only way to model these effects is to use sophisticated computational fluid dynamics simulators, but the problem is that they take several hours of compute and they are trajectory dependent.
Yes.
Every time you fly a lap, you fly different trajectories. No way you can do this in real time. That's when we also started to look at neural networks to model these effects. So we were actually moving in different ways. So the project scaled up to 10 people, 10 people looking at different problems. So how did we solve the whole problem? Maybe I should cut short on that. So nowadays, our controller is no longer an optimal controller like MPCC, but actually it's a neural network. We use a 2-layer, multi-layer perceptron.
Okay.
And this controller is trained with reinforcement learning in simulation and is then fine-tuned offline with data collected in the real world with motion capture systems. Okay. After the fine-tuning, we are ready to deploy the entire system onto the real world on a real drone using only onboard sensors. And we can fly at superhuman speed and beat the world champions by half a second, so 0.5 seconds. How did we do that? And why does it work? So now let's go to the finding. I mentioned this large error in state estimation that comes out from the vision inertial state estimation, that ranges between 0.5 meter and 2 meters. So at simulation time, we inject Gaussian noise into the state. So we have built our own drone racing simulator, and we fly in simulation our drone at the speed at which it's supposed to fly in the real world for that specific track. At the beginning, when we start training the reinforcement learning, the drone doesn't know how to fly either, by the way. So we are starting to learn from scratch. By the way, we use model-free reinforcement learning. Okay,
Completely
only the
ignoring the
simulator knows the
dynamics.
model. Okay, but it's not used by the neural network controller.
Okay.
But the simulator knows the model. Okay. But remember, it's the model that we capture from system ID. So there are still model mismatches, and I'll come to that later.
Sure.
So in simulation, basically you observe that the drone at the beginning makes some crazy behavior. Most of the times it just flips over and it crashes onto the soil. And it does this for many, many, many times. So actually the simulator takes about 200,000 iterations where we simulate 100 drones in parallel, placed randomly along the racing track that try different things. And the reinforcement learning agent is trying to maximize a certain reward function that consists of different terms. These are very important because, as many reinforcement learning people know, designing a reward function today is an art. And that's where actually most of the programming skills are now when you use RL. So one term of the reward function is that you want to, of course, maximize the progress towards the finish line. As simple as that. Very sparse objective.
Okay.
The second term is penalize crashes with gates and with the environment. The other term is enforcing or making sure that rewarding trajectories that are smooth. And the fourth term, and that's super important, and that allows us to actually find a solution that is flyable within 50 minutes, is what we call the perception-aware term. That's what we haven't talked about. So far we were talking about state estimation, planning, but there is another aspect that actually plays a very important role in all flying drones at high speeds, which is perception awareness. Mm-hmm. So everything makes sense when you fly vision-based if you can make sure that your state estimation is always reliable. But if you fly that fast, state estimation is no longer reliable because you're going to be subject to motion blur. How do you avoid motion blur? Well, certainly not by increasing the frame rate, because by increasing the frame rate, what you do is that the images become darker and darker, because to increase the frame rate, you have to reduce the exposure time. So less light comes to the lens, so the images become darker and you don't see much.
There is a fundamental limitation.
There is a fundamental limitation there. So, but what can you do? Well, you can fly trajectories that reduce motion blur. We call them perception-aware trajectories. Okay. How do humans fly? We started the collaboration with humans, a neuroscience study, and we discovered that humans fly and they try to keep often the center of the gate into the center of the image. Why? Because this way, that's the way images are sharp. You don't look away. Mm-hmm. You try to keep the gate in the center of the image for two reasons. On one side, because you need to pass through the gate, but also because you want to ensure that the images are as sharp as possible.
And is there any time where the human also looks at other gates?
Indeed, that's what you observe. Humans are not just looking at the next one gate, but they look ahead in a receding horizon up to 2 or 3 gates. Okay. They try to do some receding horizon planning.
Okay.
While machines are much better because they can actually plan globally, right? But anyway, so yes, we added a perception-aware term where basically we ask the RL agent to try to keep the angle of viewing of the camera with respect to the center of the gate as close as possible. Mm-hmm. But the RL agent will find out how small this angle should be, because actually it's state dependent. Mm-hmm. Yeah. You cannot really enforce it, globally. It is state dependent. And then it's beautiful to see that basically it learns a policy that is perception aware, and it tries to pass through all the gates in minimum time. But remember that there are still some inconsistencies because the RL agent is trained in simulation, and simulation doesn't capture all the non-idealities and idiosyncrasies of the real world. And that's where now another universe opens. What are these idiosyncrasies of the real world? So state estimation is inaccurate for different reasons. It's not just Gaussian noise. There are systematic errors. So the drone has the camera and IMU on a different frame than the propeller frame. This is done to avoid that vibrations from the propellers are transferred into the cameras, making the images look, weird, and also causing, vibrations into the accelerometer that could disturb the estimation. So, in order to alleviate that vibration transfer, we use dampers between the camera frame and the propeller frame.
Okay.
But dampers basically deform subject to the accelerations that the drone is subject to. How much are the accelerations that the drone is subject to when flying at speed, at this acceleration? Up to 5 Gs. At 5 Gs, basically what you observe is that these dampers deform by up to 1 centimeter. How much does a 1 centimeter displacement in the camera frame with respect to the body frame induces on the estimation? Up to 1 meter error of additional,
Wow.
up to 1 meter of additional systematic error that you cannot predict. It is state dependent, trajectory dependent, and viewing direction dependent.
Yeah.
Oof. So many things to take into account that are very difficult to put into, our simulator. Very, very difficult. So what do we do? When we fly the policy for the first time in the real world, the same policy that was trained for the first time in simulation, it flies in the motion capture, so using near perfect state estimation. And we do this to basically capture residual effects that we cannot capture in simulation, which are the degradation of the state estimate and aerodynamic effects, this turbulent flow.
Okay.
When we fly for the first time the policy training simulation in the real world, basically, and we are using motion capture, what we do is that we measure the discrepancy between the ground truth executed trajectory and the desired trajectory according to our internal model of the simulator.
Okay.
And then we use a Gaussian process to model this, the effects,
Wow.
both the residual of the estimation and residual of the aerodynamics. And when what do we do? We go back to into the simulation. We add this residual that were captured by flying only 3 laps in the real world. Of course, they are only for that specific racing track.
Okay.
We fine-tune the policy in simulation, starting from where the simulation had finished for the first iteration. And after a few minutes, we are done. It converges. Then we go back to the real world. Now we can finally fly the policy in the real world. And that's when we beat the human.
Fantastic. Amazing.
So what we are doing is sim to real to sim to real. So the 2 key enablers of beating world champions in drone racing using onboard vision-based sensors, what is 2 things. The realization that RL is better than optimal control in pushing quadrotors at the limits. This is a paper that actually was published 2 days ago in Science Robotics. And the other thing is that you need this additional step of data collection in the real world in order to improve your simulator with the residuals that the simulator otherwise cannot capture. And I'm afraid we have to do this when you want to push robots at the limits. So I speculate that the conclusions of this paper will also apply for car racing competitions, autonomous car racing competitions.
To other robotic platforms,
Yes,
essentially.
absolutely.
So, and what I can extrapolate also from what you say is that basically a colossal problem is robustness, as you say. And as a control theorist, we're always biased towards model-based policies. So how do you envision, guaranteeing, for example, safety in the future? This is a classic control theorist question.
I love this question. And in fact, it's a point I haven't touched yet for a reason. Well, okay, now maybe we can make a step back. So the fact that our AI pilot beat the world champions in a fair race, using onboard sensors, onboard the same, by the way, the same camera that humans were using, by the way. Does it mean that the game is over? Absolutely not. So what are the limitations? Well, why does it win? Because our machine obviously doesn't have a notion of risk and safety. So it basically shoots for the target, meaning it wants to reach the finish line, in minimum time. It doesn't want to be robust. Robustness is certainly not taken into account here. But that's where humans actually shine. They want to fly cautiously most of the times. So at the moment, we don't have a measure of risk. Indeed, you are right. So any little, deviation that the RL or the agent makes can cause a crash into the gates. And we had a lot of crashes. Still, we report that we won 15 races against 25. So we had more wins than the pilot. But remember, we were flying in a controlled environment, in a hangar, which was closed with closed doors and so on. So if you port this outdoors, there are other problems like, again, unmodeled aerodynamic effects, turbulences, other things, illumination changes. Oh my God, that is something that also is difficult to take into account. Why? Because remember, our gate detector was trained with the same conditions that you would see then at deployment time. And if those conditions are no longer violated, then it would also fail there. So there are all these things. But about safety, there is a problem. So at the moment, the drone doesn't have a measure of safety and of risk. We started working on that, though. So if you had a measure of risk, what could you do? So that's the moment of question that we tried to answer in a recent ICRA paper this year. So if you had a measure of risk, which we don't have, though, then what you could try to do would be to modulate the maximum thrust that the quadrotor can execute in order to limit your range of behaviors. So we started working on user-conditioned neural network controllers. What does it mean? The problem with the standard neural network controllers is that they are monolithic. That means once you train them, they are trained for that specific platform, for that specific task, in that specific environment.
Yes.
But what if you could add a user input that tells you, adapt, please, the neural network behavior for this specific input that can be task-dependent, platform-dependent, environment-dependent. Well, the computer vision community has been doing this for a while, conditioning the neural network behavior based on images. And the interesting thing is that the user input is an image. So we are talking about more than 300,000, values. So what we started doing is conditioning a neural network controller on a continuous input defined by a user. And we were conditioning on two things. The thrust to weight ratio of the drone, which can basically limit the maximum acceleration the drone can achieve and therefore a maximum speed and range of behaviors, but also the viewing direction of the camera. You can condition also this in order to be more perception aware or less perception aware too. And we found that this actually leads to behaviors that can be made safer, provided that you have a measure of risk, which we don't have yet. But that's something that we are also looking at.
So is it conceivable in the future to have in your reinforcement learning policy also rewards that take into account the risk, essentially? So
yes, absolutely. There are also these things. We are already working on this. I can anticipate that there is also adversarial learning, where also you try to learn an adversarial behavior that tries to modify the environment by perturbing the gates and other effects like turbulence and so on, in order to allow the RL ego agent to discover behavior that potentially are more robust when deployed in the real world. Tesla has been doing this for a while, for example.
And the other question that I had was regarding your comment on illumination. So for now, you've been racing inside the hangar, as you mentioned, but is it conceivable to see these races appearing now in the wild? Imagine having these gates in a forest, for example.
It is conceivable, but I cannot tell you when it's going to happen. Is it going to be in 5 years, in 10 years, 20 years? Why? So first of all, our gates were square for a reason, to facilitate the perception task, detection, and gate-based pose estimation using this PNP class of algorithms. Now, in many competitions, they don't use square gates, but they use soft gates that are basically made, they look like flags sometimes, and so on. So it's difficult to use geometry-based computer vision algorithms for pose estimation because the appearance of the gate can change under wind. Then another thing is, outdoors, wind gusts. We are also now trying to address that, by the way. We can talk about it if you want. And then there is another problem, which is illumination effects. This is actually one of the biggest problems of computer vision that prevents, also deployment of autonomous self-driving cars, because illumination conditions vary a lot between different times of the day and different times of the year. They have to do with the fact that okay, again, there is always some parasitic blur effect residual, because in the end, remember, you are trying to reduce the blur in the direction of viewing, but not in the periphery of the image. So depending on which features you need to localize, maybe also those features are important for localization, but actually they are blurred. So maybe you may want to fly a different trajectory. Another thing is illumination conditions. So it can change. The light can dim during the day. Clouds can pass by. Also, the sunlight can appear in the field of view of the camera, which can cause a saturation of the image. So then the out exposure controller of the camera will try to compensate for that by reducing the exposure time or opening widening the exposure time. That can cause overexposure or underexposure of some zones on the image. That can cause the loss of feature tracks. How do you take this into account? That's where now we are seeing a lot of leap forwards with the deep visual inertia SLAM algorithms, where they try to learn directly the trajectory from the images, from raw image pixels end to end. But they're being trained in a self-supervised fashion using geometric approaches still. So, there is still a reliance on geometry for that. That means that it will be difficult for them to scale in unseen conditions, so to extrapolate to unseen conditions. So again, there is a lot of things that we can learn from humans. Other things we may want to point out. I mean, human piloted drones have an IMU. So like our drone, by the way, the AI drone and the human piloted drone of the World Champions was identical. But humans are not using the IMU consciously. The IMU is only used by the low-level controller, which is the same as our AI pilot low-level controller. But in our case, also the high-level controller, the one that does a visual inertia SLAM, uses the IMU. So it uses it explicitly. So what we are also looking at is trying to navigate fly in the way that human pilots navigate, by just looking at images.
From vision.
So one day, what I hope, that would be a dream, we can do, is that we participate in a competition. We don't tell them that we have an AI pilot. We just take the goggles, we connect them to a computer. The computer receives images like any other human pilots, and then the AI navigates, by the way, also using similar to a joypad, but now controlled by the algorithm, the autonomous drone. That would be the dream. Okay, that would be the ultimate milestone. This is the Turing test
for flying, which we could coin today as the Scaramuzza test.
If you want.
One thing that I would like to talk about maybe before closing the episode concerns vision again. You are a world expert also on event-based cameras. And if possible, I would like to touch on this topic as well.
Sure.
So what is an event-based camera?
An event-based camera is a camera that has smart pixels, because this camera responds only to motion. That means that there is no output if nothing moves in front of the camera, or there is no relative motion, to be more clear. So how does it work? It looks like a standard camera with a CMOS sensor with a lens, but the output looks very different. Why? Because its pixels are smart and independent of one another. Behind each pixel, there is a microchip that monitors the scene, and whenever a single pixel detects relative motion, by basically detecting changes of intensity, possibly caused by motion or blinking pattern, then that pixel triggers an event. That's why it's called an event camera. Hey, look, there was something here, something happened, something moved according to my pixel position. Now, the nice thing is that these pixels trigger events with microsecond resolution. That means we are talking about potential update rates of megahertz. which can open up a lot of interesting scenarios for control, like high bandwidth control, high update rate control. Why is this important for robotics and control? Why? Well, and why for drones and why for cars? Because that's where actually these event cameras are actually used now a lot. Because event cameras, thanks to this working principle, which we can call differential, because they do not accumulate photons over time, but rather they monitor the scene and they tell you when there was a change of intensity. So they work in differential mode. They avoid accumulating light over time. So there are 4 key advantages. First of all, a latency with microsecond resolution. Second of all, because they work in differential mode, they have a very high dynamic range. That is 8 orders of magnitude superior to the standard event cameras. Third, they have a low power consumption because they only react to when there is motion. If there is no motion, which is typically a scene, then they mostly don't trigger anything. So mostly the camera is in idle mode. So on average, this camera consumes between 1 and 10 milliwatts, which is between 100 and 1000 times less than a standard camera. And the fourth thing is that it has negligible motion blur, because again, it works in differential mode. So there is almost no motion blur. So what are the key advantages for robotics? Well, it can in principle allow low latency, high bandwidth control. Let's think about an easy scenario. A pedestrian jumping on the highway, which we know it caused the death of a person in Pittsburgh, I think, by an Uber car some years ago. These are events that are unlikely to happen, but they can happen. Of course, there is not much that you can do in such a short amount of time, but you can try to mitigate this and maybe also use an event camera as a triggerer to have better and more robust detections, and take more informed decisions. Why? If you think of one of the leading advanced driving assistance systems, and now I'm thinking of Mobileye, which was acquired by Intel a few years back, it has a reaction time of 33 milliseconds. But often one frame is not enough to make a decision about whether you should actually trigger the emergency brake of your car. They usually take at least 3 frames. So we are talking about 100 milliseconds of time. In 100 milliseconds, a car can move by several meters, depending on at which speed you're driving. Now, an event camera can detect a pedestrian in the blind time between 2 frames with sub-millisecond accuracy, and that's what we published in several papers. So we can do what we call interframe object detection. Not only. So 2 situations can happen for pedestrians: that the pedestrian is detected in the blind time between 2 frames, so only from events, or that a pedestrian was detected from the last frame and you want to keep track of this pedestrian to very quickly track her intentions over time. So you can do fusion of RGB information from the last frame plus the events
to interpolate
that prediction. And now you can do not in interpolation, because typically these interpolations between frames are linear, but now you can do very nice non-linear fitting, because the events give you raw data. Yeah. It's like an exteroceptive IMU. An IMU is a proprioceptive, but an event camera is an exteroceptive sensor. It tells you what happens at megahertz resolution. And so that is beautiful because it can make safety critical systems potentially safer. For drones, we showed it can allow several things. For example, in a paper published in Science Robotics a few years ago, we showed that you can dodge objects thrown at the drone while the drone was flying. So in this video, you would see basically my PhD student, Davide Falanga, throwing a ball at the drone while the drone was actually moving forward, and the drone dodges it. And we show in the paper that you can do this at much higher relative speeds that you can do with a standard camera. Why? Because with a standard camera, you have the processing latency, which with a full frame, it can take, quite several tens of milliseconds. And then you need to wait for the next frame to arrive to make a more informed decision. And that frame time can take more time depending on the exposure time, and so it can vary a lot. With an event camera, you can make these decisions within milliseconds or is in a sub-millisecond resolution. Many people ask me, but why don't you just use a high frame rate camera? Now, all our mobile phones have at least a 1000 frames per second camera. So why are we not doing a high speed camera for that? Because of the so-called bandwidth latency trade-off. Because with the standard cameras, in order to reduce the latency, you need a high frame rate. But a high frame rate only comes with the cost of sacrificing bandwidth. Because at 1000 frames per second, each frame contains 300,000 pixels. So it's going to be a lot of megabytes of data you need to process. An event camera instead allows you to process events which come with low latency and low bandwidth. Because what is triggering the events is not every part of the scene, but only edges. In fact, when you look at the data of an event camera, it looks like an edge image. So only contours of people, pedestrians, cars, and so on. So only the varying visual component of the visual signal is basically filtered by the event camera. Only this is what you see. And you don't see the redundant information of uniform color regions. And that's where basically you save a lot of bandwidth while keeping the latency down.
And I have a couple of questions. So maybe just to tie it also to Agile flying, this is a technology that you also used on the drones that you used to compete against. No. Okay.
Exactly. So no, we didn't use event cameras to compete against the world champions in drone racing. Actually, we never used an event camera yet for drone racing. Why? The decision was because, well, two reasons. The first reason is fairness. Because this sensor is superhuman.
Okay.
And so humans do, by the way, it's a sensor that mimics the working principle of the human eye. So in principle, it's a fair sensor, but it's unfair to a drone pilot because the drone pilot is not sitting on the aircraft. It doesn't see with its own eyes. It sees through a frame-based camera that is transmitting images.
So it would be an unfair
in video streaming
competition.
So it wouldn't be fair. And second of all, well, these cameras are quite expensive, $5,000 for each camera. So if you put one of these and you crash a drone, and by the way, we crashed hundreds of drones to succeed in drone racing. So you don't want to definitely lose this camera. But now we are making a lot of strides forwards. We already started now flying Agile with event cameras. And we also built a very accurate simulator of event cameras that simulates also all the non-idealities of the sensor, also thanks to the collaboration with Professor Toby Delbrook, who invented the event camera in 2006 and is still here at the University of Zurich. And so we have better simulators. We started flying agilely, so not just for dodging bolts, but also for making drones safer. For example, one thing that has happened a few times around the world is that quadcopters flown commercially had a motor failing for whatever reason. In this case, what happens is that you can still do unstable hovering with 3D propellers, like demonstrated by Raffaello D'Andrea, I think more than 10 years ago, provided that you have accurate position reference from GPS or external sensors. We tried doing that with a standard camera, and it works as long as you have a low motion blur. Why? Because when you start losing a motor, then the drone starts spinning on itself like a ballerina because of the principle of conservation of the angular momentum. And then images by standard cameras get motion blur. The motion blur is ideally zero in the center of the rotation, but it's larger as at the distance from the center of rotation. So what you observe is that if you run any visual SLAM algorithm, the features tend to group in the center of the image, but this is not sufficient to do state estimation. So the drone drifts and crashes. But with an event camera, there is no motion blur. And therefore, what you observe, if you look at our video and paper, is that the features are very well distributed, and we can keep track of the state of the drone while the drone spins on itself. And we can not only control the drone while doing unstable hovering, but we can also do unstable trajectory following.
That's incredible. Of course, I should mention that there will be links in the description of the episode to all the works that we mentioned so far. There is also an event-based vision survey that you published maybe 2 or 3 years ago.
Yes.
There will be a link to that as well in the description. Maybe before we close this episode, I wanted to ask something specific about event-based cameras, because those sensors essentially output something that is a trajectory in space-time, whereas mostly our control algorithms do not really deal with that. So do you envision a new class of control algorithms specifically targeted to event-based sensors in the future?
It's a very good question. So let's clarify. Event cameras output events. The trajectory of objects in space and time is done only via another algorithm, computer vision algorithm. For example, if you want to track a pedestrian in space and time, you need to devise a pedestrian detector and tracker for doing that. But so the raw output are just pure events that contain both the target that you want to track and any background motion. Now, the key potential which requires the paradigm shift in control and robotics is the fact that these events are coming asynchronously. There is already a class of algorithms called event-based control. So in principle, the theory already exists. What the problem is that these events are coming with the resolution of microseconds. And it would be beautiful if you have hardware and algorithms that can update the control commands of your platform robot at the resolution of the single events. That's what our brain does, by the way.
Yes.
At the input, there are spikes. So our eyes produce spikes, and those are processed by different ganglion cells and other brain cells, and then are converted into an action command to our fingers and so on. But actually, in the input, it is a spike of events, a train of spikes, we call it. So we need a revolution on the hardware side and on the algorithmic side. We need hardware that can handle asynchronous events, and we need algorithms that can handle that too, that can therefore are on this hardware. There is a class of hardware and algorithms that can already do that, and it's called the spiking neural networks for the algorithm part, and there is the neuromorphic chips for the hardware part. And there is actually quite a lot of literature as well. It's already more than 20 years of research in spiking networks and spiking chips, and we are lucky in Zürich to have some of the best expertises. So here I would like to thank Professor Giacomo Indiveri that has been working on spiking network and neuromorphic chips. So just to mention a few ones, for example, the Intel Loihi chips and also Spinnaker, also the spec from Synsense and others. So they are already hardware devices that can run these spiking networks that are basically a different type of neural networks that works by activation potentials. And they can actually be activated asynchronously depending on which pixel was activated. Not only are they activated when the potential reaches a threshold, but also when a certain number of spikes enters into the membrane potential. So there are different parameters that you can tune, and these are bio-inspired because they mimic our understanding of the human brain. What is the problem? The problem is that while their promise is to be low latency, low power, and high update rate, so high bandwidth control promise, unfortunately, the performance is not the same as a standard neural network. So if you want to use it for tasks, or computer vision tasks like face recognition, pedestrian detection and tracking, at the moment they do not shine, they do not reach the same level of accuracy of standard neural networks. The problem is simply because still backpropagation is not completely solved, and there are other issues in modeling these networks that are also trained at the moment in simulation, and so there is a sim-to-real gap there too. But they hold a lot of promise for control. So 3 years ago, we started a collaboration with Intel Neuromorphic from Munich, Professor Julia Sandamirskaya, who is a professor at the ZHW, which is the Zürich University of Applied Scientists. And we used an Intel Loihi chip installed on a copter to do a reflex control task. The task was to basically mimic the rotation of a line where the visual stimulus was being triggered by an event camera connected to an Intel Loihi chip, a neuromorphic device, running a spiking network. And we showed that for the first time you could do actually this reflex control task with latency that was below a millisecond. Actually, the biggest latency was coming from the mechanical latency of the platform. Of course, the smaller the platform, the lower the latency typically. So, but this holds a lot of promise for two reasons. You can do high bandwidth control, which is very important for many platforms. Not only for robotics, it's also important for prosthetic devices. And that's also something I was surprised to learn recently. But in many prosthetic devices, for example, when you wear a prosthetic limb, you want to be able to update and send control commands with high control bandwidth. And now more and more prosthetic devices have been embedded with vision sensors in order to have an awareness of the environment around yourself. Because when we grasp an object, we look at the object and many things. And so having an enriched sensor also on your limb would actually be helpful. And so if you can embed this with an event camera, then provides a high bandwidth control commands can only be a plus.
Well, I mean, it's very inspiring and leads me to the last couple of questions just before closing the episode. So one of them is regards the future of robotics, the future of drones. What do you see ahead as, the next technologies or the next big thing that we should look at?
Difficult question. The next big thing. So I always have a look at new sensors. I'm not saying the event camera is the answer, is an enabler. I bet on event cameras, but there are many other sensors out there, and also many more that I don't know about. So, for example, radars now are gaining popularity again. And there are people looking at radars because they can see, of course, in the darkness, in hail, snow, and rain, where actually not even LiDAR can see. Also, they can see in the fog, where LiDAR cannot see. Radar is a very complex sensor to use because of all the interferences that you detect. Multipath problems and so on, but also because it's so challenging, it's so fascinating. And what I didn't know is that there are so few roboticists working on radars. And so that's something to definitely look at because they're getting smaller, cheaper, low power, meaning that the signal to noise ratio is becoming bigger while maintaining low power. So it's certainly something that we may put on a drone, on a mini drone, because it's not that we have to build drones and mimic human pilots. So we can also have superhuman drones that use multiple sensors. That's actually would be the best, to have a drone that can see in any conditions for whatever use case you want to have. Regarding vision sensors, I'm thinking about thermal cameras. They're also little explored in robotics. Also, I'm thinking about programmable cameras. I'm thinking about the SCAMP sensor. Not many people know, but this is something that is more known in the chip design community. It's a camera that has programmable pixels. You can even program the pixels to react to illumination like an event camera, or you can learn actually how the behavior of these chips should be depending on the scenario. That will basically revolutionize everything. And so I'm hoping to see some leaps in that direction. What else? On the hardware side, we also are witnessing more and more co-design. So designing parallel design of software and hardware at the same time. Of course, there, if you have FPGA, you can design algorithms that can run properly on FPGA. But so basically class of algorithms that are specific to an hardware for a specific type of sensors and so on. So for example, IPU computing platforms from GraphCore are actually asynchronous. It could be ideal for event cameras, besides only FPGA or spiking networks and spiking chips. So there are many things that are happening. We just have to venture into, outside of the comfort zone and look at what is happening in other fields. I like to go a lot to vision conferences because there is a lot of contamination that we as roboticists can get from vision.
How do you feel about the branch of robotics called soft robotics? Is it something that piques your interest?
Beautiful. I've been thinking about also starting some soft robotics, and sometimes I'm discussing ideas with Professor Robert Kachman from ETH. It's beautiful. I think that in the future we will see, some robots will be soft. I mean, I don't see hard, rigid robots. I actually see only soft robots in many, many things. So that is certainly something that is going to happen. They are very difficult to model, and you need a lot of sensors. That's where event-driven sensors are also very useful in soft robotics. I would like to mention Professor Daniele Pucci and Chiara Bartolozzi from the Italian Institute of Technology, who are also working, besides other things, on event-driven skin that basically mimics the skin of animals and humans. That is actually, it's triggered by an event. If you keep pushing your skin constantly, you don't feel it anymore. Yes. So it's really truly event-driven, and also there are some millisecond latency. So these things are happening. And they can revolutionize, robots, because if you have an intelligent skin, then you have a safer robot for industrial settings.
This is truly inspiring, and leads me also to the last question of this episode, which is trying to inspire future students. So normally we like to close the episodes with advice to those who are venturing into the field, say of robotics or control. If you have any piece of advice, what would you give to a new student?
My main piece of advice is to venture into the impossible. That's a quote from Arthur Clarke, the great, one of the greatest science fiction writers. But it was also my philosophy when I entered the field of magic, because that's what magic tries to do, to basically do the impossible. I think everything is possible, and often what keeps us away from doing things that appear impossible is our fear of exiting the comfort zone. So I would say I recommend all young PhD students to try to exit their comfort zone, try to look at the key challenges around us, start from real world problems, and how we could address them. And I think any person from any location in the world can make a big change for our world, because, for example, let's think about self-driving cars. If you only test your car and do research in Phoenix, that is in the middle of the desert, and it's one of the sunniest places on Earth, you are never going to encounter so much rain, hail, and snow as you would see, in other places. Or, for example, if you instead are researching in India, you will have the chance to have, a very crowded scene with a lot of traffic and crazy cars that traverse the street here and there. They will not see, for example, in other cities in the United States. So look around yourself, look at what are the opportunities that are around you, and try to make basically a change. Look at what standard algorithms have done, and try to basically break them into, decompose them into different subproblems, see where they actually test them, re-implement them, see where they break, and try to basically use these failure points as an inspiration to find new problems to solve. So this is basically my piece of advice.
Well, Davide, it's been a real pleasure to have you on the show. Thank you so much for joining us.
Thank you. Thank you very much.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.